Okay, so before we ended the electron migration part, we are going to give you an example here. Here what we have is EM-induced voiding. So in the beginning, we have a material, is alumina line with a 0.5 times 5 micrometer, and the effective passivity equals to 10 to minus 15, and the effective diffusivity actually means the exactly diffusivity of this alumina. Usually, effective diffusivity is how we get the effective diffusivity is we measure that by some method, then we can get the real diffusivity of these materials. So the effective diffusivity of this alumina line is like this at 115 degrees C. So the question here is, please estimate the time required for forming a void with this size 0.5 times 0.5 times 0.5 micrometer at the cathode size of the alumina subjected to an electrical current 2 milliamp at 115 degrees C, and also give you some relative information you probably need for these questions. So the most important part is after applying an electrical current, and you are going to observe a void form at the cathode. So based on these descriptions, you can know that this void formation is due to, because you got a void form at the cathode, right? So it implies that these materials have subjected to electron migration effect, right? So when you try to draw the pictures like this, alumina line and with the 5 micrometer times 0.5, and we got a current passing through with 2 milliamp current, right? And so the electrons flow will go this way. And why I know there's a EM effect? Because it said there's a void form at the cathode. Based on this informational clue, and I know there's an EM effect, and this void definitely is EM-induced voiding. Okay, so now how much time required for forming this void? So how much time? So based on the time, so you need to think about in order to calculate or estimate the time, you need to know the flux. So the void formation, so you need to know the JV, right? So how to estimate the time required? So first of all, you need to know the size, the diameter of this void, and divided by what? Divided by, if you can know the vacancy flux, right? As long as you know the vacancy flux, and you times the flux is the numbers of vacancy per second per area, you times the area and also the atomic volume, then you know the total vacancy form per second, the total size of vacancy form per second, right? Or per unit time period. But some people probably will ask, vacancy flux, how to know the vacancy flux? Here, right? So in this case, the vacancy flux actually, the value of the vacancy flux is the same with that, with the atomic flux, right? But the only difference is what? The sign, the direction is different, because the one we deal with is a pure material, is alumina line, right? So if you have the JA here, then you got the JV with the same value but with the opposite direction. So here we use the JEM, actually we use the JA atomic flux times the area times the atomic volume to get this value. Okay, so this JEM actually is a number of atoms passing through a specific area, right? And per second, then you times the area and you times the volume, so you know the diameter of the void form per second. Then you divide by this value, you got the t, right? So in order to get the time, you know a, right? A is here, omega is here. So the one you need to know or calculate is the JEM, is the atomic flux here, right? So how to get the atomic flux? Based on previous slide, you know will be the mobility, concentration, and the driving force. Mobility here, we will use the diffusivity divided by kT. Diffusivity, we use the effective diffusivity here. And concentration of alumina, if you check all the information, how to get the concentration of alumina, it didn't give you directly, right? The one you know is it is a pure alumina line, and it give you got omega average atomic volume. So based on the information you learn is atomic fraction equals to average atomic volume times the concentration. And here you know it's a pure alumina, so this is 1 divided by the omega, so you got the concentration, so put here. And the diffusivity part, you got here, and the K is here, and T, you use the absolute temperature. So in order to in order to confirm the unit you used for each term are correct, so please label. You could write somewhere. You need to use the unit check. Okay, for example, like the diffusivity, you put a value here and put a unit here. Then when you try to write down the K, you put the value here, right, and the unit here, and the K here. So after you list all the values, and after you check the unit, then you can confirm whether the unit you put is correct or not. And the beta here, beta is a minus 10e, so you use the beta. And JE is the current density, so it gives you the current. You need to divide it by the area, you got the density. And also this one is the electrical conductivity. Electrical conductivity we could directly put here, and also put a unit here. So after calculation, you got the value for the flux is like 3.4 times 10 to 10 per second per cm square. Then you take this value back to here. Okay. Oh, okay. So before we put here, so you need to do the unit check. So delete some part. Then you can confirm whether the unit actually is the correct unit for the flux. If it's correct, you just put the value here. Then you can get it's around like 8.9 times 10 to 7 seconds. Okay. So this is the examples, and some people probably will ask about related to the beta equals to minus 10e here. The beta here actually means the effective charge of alumina, so it's a negative, right? But here actually it should be the vacancy flux, right? So the difference between the vacancy flux and the atomic flux or alumina flux is the sign. So here I didn't put the minus here. Minus here, due to the one we want to put here actually is the vacancy flux. We just calculate the alumina flux to substitute to replace the vacancy flux. So the values are the same, but the sign are different. So we didn't put a minus here. Okay, just remind you. Okay, let's give you a summary of the electromigration. What's the electromigration? Actually, it is a close effect between the diffusion atoms and the electrons flow through the momentum exchange. And in order to deal with this kind of electromigration phenomena, first of all, you need to identify what kind of materials you are dealing with. For example, like in the beginning of these sections, we talk about ionic material, right? And it's a doped ionic materials. And ionic material doped with positive charge ion, right? So in that case, as long as you apply the electrical field, then you can measure the electrical conductivity, right? Or you say by changing different concentration and dopants, you can tuning or control the electrical conductivity of that type of ionic materials. And after that, we move to the metals. And in the metals, there are two different types of metals. You can consider that as different types. The one is we have the doped metals, doped with some interstitials. So in this case, when you apply an electrical field on this kind of material systems, the atomic flux of these interstitials can be expressed into two parts. The first one is due to the concentration variation of these interstitials, and the second part, mobility, concentration, and driving forces due to the electrical field applying on these materials. And the driving force here, we use the beta E to represent the driving force. And we also show you how to define or determine the value and sign of the beta. And the physical meaning of the sign of the beta is if the beta is negative, which means these interstitials moves to where? Move the same direction with the electrons flow, right? But if the sign of the beta is positive, it means these interstitials move the same direction with the current. So the sign of the effective charge implying that the direction of that the interstitials moving. And the second material system also in metals is we deal with is the pure metals. And the diffusion mechanism of these pure metals majorly rely on the vacancy-mediated diffusion mechanism, which means these substitutional atoms or the atoms at the latest point diffuse or exchange the location with surrounding vacancies. That's the way how these atoms diffuse. In this case, the atomic flux, in order to know the atomic flux of these substitutional atoms, we try to first of all because the concentration of these substitutional atoms, you can measure that for sure, right? But mobility of these substitutional atoms is very difficult to measure, right? Because you don't want to label them by like the isotope or something, so very difficult to get the mobility of these substitutional atoms due to these reasons. So but we still want to know the JA, right? So by calculate or measuring the JV, then we can get the JA. This is for this case we just do this way. So what's the JV? Is the vacancy of the flux. Vacancy flux. So will be also expressed like the mobility of the vacancy, concentration of vacancy, and the driving force here. And the mobility mobility of the vacancy, because we can visualize the vacancy by different types of material analyze tool, right? For example, like SPM, right? So you have chance to know the mobility of vacancy and the concentration of vacancy. You also can estimate that different types of materials analyze tool. And the driving force here is because it's the EM. That means you observe the EM, right? Electron migration means the current density is quite large under these situations. So the driving force here, beta E, beta VE, actually is the same idea with what we show you in the interstitials, but we label V means the effective charge of vacancy. In most of cases, this value is positive, and in most of cases, this value is negative in metals. Okay, it has different sign for the value. Okay, so the third part will be the electron migration flux can be counterbalanced by the flux driven by the concentration gradient or stress gradient. So this is just give you a hint. As we know, we don't want the electron migration happen in our materials, right? So how to avoid that? So here, just give you two hints. Probably, actually, there's a concentration gradient can counterbalance the EM effect. A stress gradient also can some part counterbalance the EM effect. But however, if you try to continuously increase the current density, you need to, under these situations, then concentration gradient and stress gradient may not be well counterbalance or totally counterbalance the EM flux. You need to think about other ways. So we are going to show you how to, do we have any chance to counterbalance the EM effect, okay, in the following slide, in next section something. Okay, so let's give you a quick summary here. The electron migration, the difference between the electron migration versus the thermal migration. For the electron migration part, we know it only happens when the current density is very high enough. Under that situations, then the driving force for this the driving force acting on these diffusion atoms can be expressed like the minus beta electrical potential gradient, and the atomic flux due to induced by the EM can be expressed like the mobility, concentration, and the driving force. And just a quick reminder, the difference between the driving force, you can observe some difference, right? In the last part, in the lecture 1, we also learn if you apply the electrical field on the materials, then the driving force F small q can be expressed like will be equals to minus electrical potential gradient, right? But in that case, we don't observe any electron migration. That means the current density is low compared to this one. So as long as you figure out as long as the current density increase and we observe the EM effect, then when you try to write down the driving force and atomic flux driven by this EM effect, should be put the effective charge to modify the driving force part and also the atomic flux. Okay, so today we end it here.